Hello and welcome to the lecture on signal processing within the course series on computer graphics at KAUST. Today we will be dealing with a topic that goes across any research direction or technical branch, which is dealing with a signal that is somehow processed on a computer. The signal can be of various origins. However, on the computer, we rarely can represent the signal in a continuous way. And therefore, we represent it as a form of discrete samples that represent the continuum. These discrete samples can be then used for reconstructing the function as in its continuous form, or for representing it as another set of samples because of, for example, displaying it on a hardware which has discrete set of pixels which are depicting certain signal. In computer graphics, we will be mostly dealing with images which are finally rendered, and there we have an example of a discrete representation of a otherwise continuous scene. But this is not the only example. We can also think of input of a camera where we have a sensor with a limited amount of sensing units, which are then sensing our continuum, our nature or the particular scene, and turning it into a set of samples which represent it for us. However, sometimes we do not want to see the resulting image in exactly the same resolution as the camera captured it, and we would need to resample the image to another resolution. Another example could be, for example, just a digitizer, like my pen, for example. While I am drawing here a continuous line, which you can see on the slide, the screen itself has a discrete amount of samples on which it's sensing the position of the pen, and based on these samples, it then reconstructs a continuous function. Another area from the medical domain could be the medical CT, which reconstructs the 3D scene, a human body, for example, from a scanning process, and it creates not a two-dimensional array as an image, but actually a three-dimensional array of so-called voxels. So we can see that when we are dealing with digital representation of reality or of a virtual scene even, we often represent it as a set of samples. And to understand how to represent it in a correct way in order to avoid certain misbehavior, this lecture will give us the great insight from the theoretical point of view. So generally, if we have a signal, we can represent this signal only to a certain detail on a computer. We cannot have infinitely detailed signal representation. For example, therefore, a sharp edges, so discontinuities in the derivatives, would be very hard to represent in with a as a function through a discrete set of samples. Therefore, the function often is somehow prepared for being able to be sampled by and represented by this discrete set of samples, and this is called band limiting. So the continuous function first, in order to be representable by samples, can be band limited. We will be talking about that later on. And then when we sample our continuum, our continuous representation, we should adhere to certain rules. So, for example, there is something called the Nyquist frequency or Nyquist limit, And that tells us that if we have a certain signal, which is represented by a set of frequencies, as we will be talking about later in this lecture, then the sampling should be double the highest frequency which is represented in the signal, at least double, so that the signal can be represented or reconstructed from these samples without any artifacts. If we are undersampling, meaning that our function has higher frequencies and we are not having enough samples, we will naturally lead to some artifacts, various types of patterns will be showing up, which are actually not in the scene and are caused purely through this sampling and reconstruction process, which is misbehaving. We can see that here in this drawing of one signal, which is the continuous signal here, which would be this sine wave. And you can see that if we are simply having enough of samples, then like it's in the first case, then and we simply just connect these samples. We will talk about what is this just connect from the theoretical point of view in a moment. Then we see that the function will result in a similar function as it was at the in its original continuous form. So the samples are representing this function sufficiently. The situation is quite different at the bottom in the second case, where our number of samples is much more limited. So while we are having here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 samples, we have only one sample per such an interval of 10 samples. So this is heavy undersampling of this function. So we have been putting a first sample at the beginning, then the next sample is here, and then the next sample is here, and the next sample is here, and so on. And you can see that this is a representation of this higher frequency sine wave, which is not sufficient to reconstruct the original function. And actually, instead, we will be reconstructing a function which is entirely not present in the original representation. So our reconstruction from the samples will likely look like something like this. This is not a pattern which was seen, this is not the pattern which was present in the reality before it was sampled, but due to our lack of sampling, we have been able to represent this signal with a totally different signal, which would be very wrong. And this is an artifact. And we will see such artifacts happening. We will call them moire patterns, for example, or other edges and so on, which will be corrupting our resulting image quality due to the sampling and reconstruction wrong designs. There are some examples about aliasing effects. First, let's have a look at this moving one. You can see that the scene is gradually getting faster and faster, and now we cannot. And suddenly, what we see that the wave, the green wave, is moving in the opposite direction, and then suddenly it is moving in a again yet opposite direction. And what is this? This is an aliasing effect over time. This is also called the stagecoach effect, and I will be mentioning that later in this lecture. The second effect, which you can often see, is the so-called moire effect, which is not of temporal origin artifact, but of a spatial origin. This moire effect has coming from a result when we are resampling an regular pattern, some regular pattern, onto another regular pattern of our sensing unit, and suddenly some weird patterns are occurring which are not part of the data, but due to the poor reconstruction and sampling, they will be suddenly appearing. This is exactly the same as the sine wave, which has appeared from the previous image, which was of much lower frequency and was not part of the reality. However, it showed up as being one. So this is exactly the same problem of low sampling rate. Okay, but before we can understand the sampling and reconstruction thoroughly, we need to introduce certain mathematical frameworks which help us understanding this sampling and reconstruction problem. And the central function or tool which is used to explain or to carry out the sampling and reconstruction is the convolution. Convolution operation is a mathematical operation on two functions which produces a third function out of these two functions. And it can be an example of a convolution, can be an convolution filter, which is used in image processing, or we know now about convolutional neural networks, that the convolution plays a very central role. We can also understand the convolution as for example, the example of a moving average. So imagine we have a function like shown in this image, and we would like to understand what is a moving average of this time series. So let's give here the t, because this is time series. So if we want to know what is the average over a certain time, maybe a day or a year, then we simply integrate this function to obtain the area under this under the function, and then divided by the length of this interval, which will be, what will it be here? Here is x minus r, x plus r. So this will be 2r. So this is a moving average on the continuous function. And as we described it, this is one instance of a convolution. On the discrete set of samples, we can see a similar example of a discrete moving average. So where we are observing certain values within a certain range, this is again sampling over time, and we are summing up all these values together. We sum up all these values together and then divided by 1 divided by 2r plus 1. Plus 1 here because 1, 2, 3, 4, 5. Our r is 2 in this case. So we have two elements which we want to average. So this is 4 plus 1 is 5. Okay, so this is one example of a convolution, fairly simple to start with. Let's have a look at more examples of a convolution. For example, an filter which we use, which is similar to the moving averaging, which is, however, giving more weight, if you like, to some parts of its area of influence. So, for example, here we have a certain filter B, which is having these weights in the center it's 6, from one distance unit from the center it's 4, and one more is 1. So the central values are getting the most of the are considered the most. And in this case, we will be able to create some kind of averaging of these samples again, but not where all these samples are uniformly weighted, but with a different weighting for each sample. And these values are normalized by their sum. So if we now sum up 6 plus 2 times 4, that will be how much? That will be 14, plus 2 times 1, it will be 16. So if we divide it by 16, we normalize this value. So we sum up to 1 as the sum of the weights. And we can see here, this is our function A, discrete set of samples or sequence A, which is here, and is multiplied always, each element of A is multiplied with this other function, and their product is then summed up with other products of their multiplication. So here we will have, for example, the 1A here will be multiplied by 6 divided by 116, and then summed up with the rest. So this is a convolution with a specific filter. And we can see here that the indexing here is going from with some iterator j, which is iterating throughout our sum, and there we will get our values for one output I. So here, this output here is our I value, and the I value of this convolution of A and B functions is obtained through the products of its neighborhood. So J would be going within a certain range around I, and therefore, and the B minus the filter is indexed with I minus J, and this will lead to the values when, for example, J will be I, because one of these neighboring samples will be also having the value I. Well, samples, which I mean here, will be having also value I. The BI minus I will be B0. So this is, for example, the B0, number 6. B0 equals 6 divided by 16. And B minus 1 and B1 is equal 4 divided by 16. And B minus 2 or B plus 2 is equal to 1/16. So, and outside, for example, B minus 10 or B plus 100 is equal to 0. And any value outside B minus 2 and B plus 2 is equal to 0. And then we say that the function has a finite support because it is defined only on a certain compact interval and is 0 outside. So this is a typical convolution operation on in discrete case, as we will be learning at the basic image processing lectures. So let's have a look at a few convolution kernels. One is the box filter, the box filter is a uniform averaging, so each value in the neighborhood of our signal A will be weighted with the same value. That's why it's a box, because it just forms this kind of a box. And in the discrete case, the weight, which is here, is 2r plus 1. We generally are using a box with an odd amount of elements, which is then defined by the radius of such a filter, which goes from minus r to r. All the weights, if we are performing averaging, so a smoothing filter, will have to sum up to 1, so that the overall energy which is in the signal is not amplified or suppressed. Let's have a look how a convolution with a box filter will behave on a function which is a step function. So the step function is a discrete sequence which has all values which are smaller than 0. So indexes of j which are less than 0 will be equal 0, and everything what is higher than 0 and or equal will be equal to 1. So that's the step. And our filter is our box filter, which we will be using for the filtering. So let's have a look of what will be the filtering, the convolution result here after applying this convolution to our function A, to the filtering with the filter B. Well, at the position A equals minus 7, or our outcome will be evaluating the values of this neighborhood, multiplying them with our filter kernel, which is 1/5, which is uniform weight everywhere. Well, but if these are zeros, then the multiplication and sum will sum to 0. Let's have another look at another obvious example, which will be when the I is equal to 6. So what is our result of the convolution at the position I equals 6? Well, let's have a look at the original signal, and we can see that this is the position 6, and we have our filter has radius 2, so all these values will be considered in the evaluation of or in the convolution. These are all multiplied with the uniform average, which is then 1/5, and 1/5 times 1 will be 0.2, and it will be 0.2 for the central pixel or central value, and it will be 0.2 for all of the other ones as well. So if we sum up the 0.2s, then we end up with 1. So here we have our filtering has not really changed the values, because the neighborhood is constant in this area of the function. Let's have a look at I equals to 0. What will be the filtering there? The filtering there, I equals to 0, will be containing our A0 value, which is 1, A minus 1, which is 0, A minus 2, and as well A1 and A2. What will be, in this case, the result of the convolution? Well, 1/5 times 0, 1/5 times 0, 1/5 times 1 is 1/5. 1/5 times 1 is again 1/5, so we have 2/5. 1/5 times 1 is again 1/5, which in sum are 3/5. 3/5, which is equal to 0.6. If we'll do this exercise for neighboring values, we'll find out that this value will be equal to 0.4. This value will be equal to 0.2. This value will be equal to 0.8. This value will be the first one, which will be equal to 1 after filtering. And what do we see here? So far, I was telling you more or less trivial things to prepare you for something which is becoming an interesting aspect. Here, the reconstruction with the box filter here resulted in what we call a linear ramp. So I drew it very badly, but this is a straight line, in fact. If you can see that 0.2 is the increase between the samples, we have created here with this averaging a linear ramp, not just an arbitrary change from 0 to 1, as we would expect from such a smoothing filter, but actually a linear increase. And this is interesting, and we will look at it at some later point. So the convolution has several interesting properties. For example, a convolution as a mathematical operation will be commutative, which means that we have been so far talking about an input signal and a filter, but actually we can just as well consider the filter being the input signal and the input signal being the filter. So we can just exchange their roles and the result will be exactly the same. We can see it here when we will be exchanging the iterator J, which we were using in the convolution, with the values I minus K. So if we now change this iterator here to be of this slightly different formulation, then we will see that the iterator changes to K. And while here at the beginning we had this AJ, so a sample from the neighborhood of I, and weighted by I minus J, through certain substitution, we are seeing that our sum is changing to a representation where we have the iterator K and we have the BK as a sample from the neighborhood and I minus K being the filter value. So we see that this commutative law is applicable for the convolution operation. This is great. And also, another great thing is that the associativity between convolution can be also achieved, meaning that we can change the brackets of the order of how the convolution will be performed. So for example, here we can see that, let's say we have this input signal A and we are convolving it with a certain filter B, and then the result we are convolving with a certain filter C. Instead, we can just convolve these two filters, create a BC filter, and then convolve the entire signal with this already pre-computed combined filter. That is what associativity will be good for. The associativity is achieved at a certain cost, however, and that is this strange formulation that the filter is indexed as I minus k. So if our values, let's say we have a situation here, I will be 2, let's say, and k will be, so I equals 2, and k will be going from k equals I minus r to I plus r, where the r will be equal to 2 as well. So if we are now having certain filter, -2, -1, 1, 2, we have our filter here. So these are the values of our filter. Then if we are performing the convolution according to this description, then we are having our input signal, which will be the k equals now at the beginning in this sum will be I minus r. So I is 2 minus r is 2. So it will be 0. So k will be 0 b 0 times I minus k. So this is I is 2 minus r is again 2. So this is 0 minus k. How much is, sorry, and I is here. So 2 minus 0, this is 2. So we will be taking this sample and waiting. So let's say the B is a signal and it goes from 0, 1, 2, 3, and so on. If we have this situation here, we can see that we are having the leftmost sample is multiplied with the rightmost value of our filter kernel. And then we will be having B1, and it will be multiplied with the filter kernel value 1. And then the B value 2 will be weighted with the filter kernel value at 0, and 3 will be weighted with filter kernel valued at -1, and 4 here will be weighted, multiplied with the filter kernel value indexed at -1. So this order is going in the opposite direction. This order here is going in the opposite direction as we are iterating through the actual signal. And this is in order to maintain and support the associativity principle. So this indexing is reverted, if you like, but as we are most of the time having symmetric kernels, this is not an issue. If we will not have such an reverted indexing, the associativity principle will not be possible for convolution. The next law is the distributive law for convolution under addition or subtraction, where we can first perform a convolution and then sum up a convolved the results, or first perform a sum of two signals and then convolve it. We can see here an example of the associativity here in this case, where we have three filter kernels, B1, B2, and B3, and we have one signal here. And instead, this would mean that we have perform a lengthy convolution 3 times with 3 different filters always, and the output of one convolution will be input for the other one. Why don't we instead rather create just one filter out of as a convolution of the 3 filters and then perform the convolution with a long signal afterwards just once? We will save a lot of time thanks to the associativity principle. Now, mathematical operation of convolution will have a identity as well, and the identity for operation for convolution will be convolution with a discrete impulse. We can see there's a very trivial filter kernel where the filter kernel is only defined at B0 is 1 and B I unequal 0 is 0. So this filter kernel is everywhere 0, only at 1, at 0 it is equal to 1. And if we are filtering with such a filter, our input signal, we will basically just be multiplying the currently processed central sample with 1, and all the other neighboring samples we will be multiplying or weighting with 0. So it will be an identity transform. You can say, is this a big deal? Well, from a mathematical perspective, identity operation is important to have a defined for a certain operation. And also it can be practical. So for example, here you can see that what we want to do is to create and subtract from our signal A and a signal which is convolved with the same signal but convolved with the filter B. This will be, for example, used in sharpening operations where we are subtracting certain blurriness from our image. So this could be a convolution smoothing, and if we subtract smoothing from an original image, we are somehow sharpening the image. And in order to perform such an operation, we can also reformulate it thanks to the distributivity law that we have this A we will represent as a convolution with a identity convolution, so with this filter, which will be again A after the convolution. But thanks to the distributivity principle, we can now reformulate it in such a way that we have our input signal, and then we have a new kernel, which is then computed as the subtracting the B filter kernel from the identity filter kernel. And this will be a component-wise subtraction. So this would mean that, for example, D minus 2 minus B minus 2 is equal to D minus B at minus 2, and so on. So it will be always, here will be always 0, only if the iterator will be equal to 0, it will be 1. Okay. So now we understand a convolution as a weighted sum of our input signal. This is one way how we can formulate it. Another way how we can formulate convolution is actually, so in our previous originally defined um, approach to convolution, we would be putting our filter kernel at a centrally processed sample. I will just draw the previous approach here. Something like this. This is a central value, and I'm drawing a continuous kernel, which should be maybe discrete. So far, we have been talking about discrete, both kernel and signal. And then the magnitude of the filter kernel at the position aligned with the sample, the amplitude of that filter kernel will be defining as how much is that particular value contributing to the output value. So this is the previously defined way how we are convolving the signal with the filter kernel. But there is a different way how to formulate it, entirely equivalent, that we are putting the filter kernel on each contributing sample from our neighborhood. So we are here filtering at this position, and we are putting filter kernels at all these positions, and we are scaling our filter kernels with the value which is at that particular location. So, for example, this value will be the A5 will be the top of our filter kernel placed on that position, and the A6 will be the top of this filter kernel. They are all the time same filter kernel, just scaled version of it. And now, if we want to know what is the value at this particular location, then we simply sum up what are the values of these filter kernels which are extending over our output position. So at the output position 7, we will then have contributions from this filter kernel, so this is one contribution here, another contribution here, then this filter kernel, which is this value, and then another contribution from this. Oh, and this filter kernel actually is contributing here. And this value, although it is very high, its contribution will be not so high to our final value. So we sum up all these values which are here, and we end up in the resampled value. So this is the way how we can perform the convolution as a sum of shifted filters. And these shifted filters are weighted by the values of our neighboring signal values. The shifted filter here is exemplified on this signal. So this looks like a signal, but it is also a filter. It's the filter BI, and this shifting operation by 3 is depicted here. So you can see that this value is the same here. We are shifting by 3, 1, 2, 3, in this direction, in the right direction. So this is the shifted filter operation, and we can shift the filter by different amounts, 3, 2, 0, -2, -1, whatever, and then multiply our shifted filter with the actual value at that location of our input signal. And by this we can perform the convolution using this sum of shifted filters. Okay, we have been discussing the discrete case until now, but convolution is defined also on continuous functions. So a continuous input signal and also continuous filter kernel. For example, here we can see that our filter kernel will be this value ft. So ft is our filter kernel now, and our g is our function. Well, one can define it as a filter kernel or as a function or interchangeably. As we know from the commutativity principle, it doesn't matter. But what is the interpretation of this convolution operation? So if our position of our x, so x value here, if we perform convolution here at this position of these two functions, what we will end up with is basically the function g scaled by the function ft. At each position, of course, this is not a sampled signal now, but continuous one, we are scaling this function. So we can see that this function here is somehow similar to the g, but it's scaled and it has a finite support. And what we calculate here is an integral of these products and infinitely many products in this case, in the case of continuum. But this is an integral, and the integral results in the sum in the area under our function. So this is the integral value, the area, and its value will be plotted in this convolved signal of f and g. If we have another position, let's say the x is here, similar thing happened. The f filter looks exactly the same at this position, but this function here looks a little bit different. Therefore, their product looks a little bit different too, but still it is having a finite support, and the area is slightly smaller, we can see, than the previous example, and therefore its value will be a little bit lower. But what we see here, that we have our signal, which is smooth, but still quite changing. Our input signal G is now super smooth because it has been convolved with this smoothing filter. And as I described to you just on the slide before, we can define this operation as a in the traditional way of defining convolution, or as the sum of shifted filters. Here there is a typo. It should have been G here, not B. Okay. Let's have a look at some functions, continuous functions, and let's have a look again at our box function, box filter, but a continuous one. So the box filter is defined as being of value 1, so this is 1, at a certain interval from -half to 1/2. So the interval, the radius is 1/2, and this is equal to 1. The filter kernel has an extent of 1, and everywhere else it is equal to 0. So this is an obvious box function. This drawing is a little bit misleading because the 1 and the x-axis is much longer interval than the one in the y-axis. So these axes are a little bit non-uniformly scaled in this drawing, but it is really a square if you will have uniform scaling along these both axes. Such a box filter or box function can be, for example, convolved with itself. We can see it here. So this is a convolution with itself, and if our convolution will be the box filter, we will realize that what happens if we are convolving with the box filter. So at this position, we already had this exercise. At this position, we will be multiplying this box function will be equal to this box function will be equal to 0 here, so multiplication with ones will be equal to 0. So at this position, we will have a value 0. And the same will hold approximately here. We will have again a value 0. But what if these two boxes are starting to overlap? We have seen the convolution with the step function, and the convolution with the step function resulted in this linear ramp, you remember? And this step function would be similar to a box filter, but it was having the value 1 for the all positive or for all non-negative values. But here the box filter is having a limited support, meaning that the value 1 is only on a limited area, and therefore we are again having a linear ramp here caused by the values which are then equal to 0, which are higher than 1/2. We can see here that what is happening for this one particular sample, which is calculated here, this one, it is again an area, right? It is an integral, so it's an area of a product of multiplications. The multiplication is basically defining as the area where these both functions are simultaneously equal to 1. So these values are now forming as a certain area. The more these two boxes overlap, the higher the value will be. So in the value 0, the overlap is the highest, and here the value will be 1. For everywhere else, the value will be something less than 1, because the integral of the entire box is 1, but the smaller part of that box, integral of that, will be something between 0 and 1. So this is an interesting development, because we have convolved the box filter with itself, and we have created another filter by that, which is called the tent filter. The tent filter has also a finite support, but its radius is 1, and its area of influence, where it is non-zero, is 2. The value of the tent function at the particular location can be computed from this equation, where we can see that it will be always non-negative. However, it will vary between 1 and 0, and when x is equals to -1, it will be in absolute values turned into 1, and 1 minus 1 will be 0. And if x will be equal to 0, 1 minus 0 is 1. So here in this location, we will have the value 1. All right. So with convolution of box filter with itself, we can create a 10th function. Interesting. We will see how other filters we can generate when we are convolving them with themselves. But here we have another representation of an identity operation in convolution in the continuous case. We had previously this filter which was having just the value 1 at 0, and everywhere else it was equal to 0. We have something similar but not exactly the same in the continuous case. We have here the Dirac delta function or Dirac delta impulse, which is defined in such a way that its value at the x equals 0 is undefined but can be understood as plus infinity, and it is 0 elsewhere. So in limit, this function is basically having 0 values everywhere, but not at the value x equals 0. But it has this key property that its integral from minus infinity to infinity, where pretty much everywhere it is equal to 0, but just at the value t equals to 0, it will have not non-zero value. Its integral is equal to 1. So it is somehow infinitely thin, but infinitely long rectangle, if you like. But it is so thin that its value at the one side is almost 0, and the other side is almost infinity. You can imagine it like that. And this Dirac delta impulse is useful in the continuous functions for defining for sampling, in fact. So the convolution of a continuous function with a Dirac delta impulse is the convolution of it will be giving us the value at this particular location of this function. Why isn't it the case that we are just multiplying it with 1 as it was in the discrete case? Well, if we are reformulating this convolution here, then on an infinitely small interval, it is this delta is non-zero. So as this is infinitely small, actually we can take out the ft at the x value. So when the delta is equal, delta is having the parameter 0, so x minus t is, sorry, x minus t is 0, so x is equal to t. Then, as we have infinitely small interval here, then we can take the fx out of this, out of the integral as a constant pretty much, and we will be integrating just the Dirac delta, which we know it's 1. So it will be then fx times 1 as a result. So this is the way how we are performing sampling with the convolution with the Dirac delta function. And we can see this, that we can move our Dirac delta from its position at so that it will be non-zero at a certain position by moving it by a certain value, like for example the value t here in this formulation. So the Dirac delta is now moved at various positions, with varying t. So, and with this, we can always resample or sample this continuous function and represent it as a sampled representation of this function. So we can already see, we are talking about samples, that this Dirac delta will have a key function in the sampling process. Interestingly, we can define convolution not only in either discrete signal and filter or continuous signal and continuous filter cases, but we can also have a mixed signal and filter setting where the signal can be a discrete set of samples, a sequence, and the filter is a continuous filter. And with this is the central operation for reconstruction. So we will have a continuous filter which will be out of our discretely defined function through samples. We will reconstruct the continuous function. And therefore, we can see that for a continuous filter and discrete set of samples, we have here a definition where our filter is continuous and it's giving a particular weight at the intersection with some integer, and this particular weight is then weighting our discrete sample, and our convolution is then sum of these discrete samples weighted by weights coming from a continuous function, continuous filter. Here we have the same convolution, but with a slightly differently reformulated convolution as a sum of shifted filters, where you can see here that while we were previously in the top case, in the first formulation, we are putting our filter kernel at the central location where we are performing the reconstruction. And keep in mind that here we are not at one of these integer positions where the sample has defined value. Here in the continuous case, the value is undefined, but yet it has a certain neighborhood which has non-zero values, and these values are then always weighted with the particular value of the filter. And so on. And it is these values of the neighborhood which are then summed up together and forming us the value at this particular location. And you can see that we have reconstructed a continuous function out of a discrete function. And by changing the filter kernel and its extent, we can achieve different quality of reconstruction. We will be talking about that in next slides. Here we have another formulation where we are placing not just one filter kernel and weighting its neighborhood, but we are placing several shifted filter kernels, and at the centered at the integer position of each contributing neighboring sample, and then we are summing up the values of these filter kernels together to calculate the reconstructed value. And we can see this is somehow a smooth filter. It's not like a box filter. It's not like the tent filter, because the tent filter has a discontinuity in the first order derivative at the value 0. This filter is continuous even in its first order derivative. And we can see that This filter here is somehow reconstructing as a continuous function, but not at this continuous function is not going through the individual samples, but somehow between them. You see, and this filter actually is a cubic filter, and it's a cubic B-spline filter. And this cubic B-spline filter is also used for the splines or B-splines in the case of curves, which will be curves defined by a set of points, and these curves will be the so-called approximative curves. So the curve will not go through the actual control points, as they are called in this in the terminology around curves, but they will be going between them in the convex hull, in fact, of the control points. So here you can see how we can reconstruct the values of our discrete samples to form a continuous function which is represented by these discrete samples. And sometimes the function interpolates the sample points, the points at the integer locations, and sometimes it does not, as for example in the case of the cubic B-spline filter. You can think of why do we want to make reconstruct a function which is obviously different from our original function, as it doesn't go through the individual samples. Well, such a function will have another advantage. It will be, for example, it will not be the same as the original function. It will be maybe a smoother version of it, which might be beneficial and will not suffer from other artifacts, as we will see soon. Let's have a look at the convolution as an operation in more dimensions. It will be practical to look at one-dimensional cases to explain the principles of convolution and principles of sampling and reconstruction. But practically, we will be, especially in computer graphics or in visual computing, we will be dealing with at least two-dimensional signals, because we will be dealing with images or even with volumes. So the good thing is that the convolution in several dimensions is defined in a very intuitive way. So in a convolution at a particular location of a two-dimensional array indexed by I and j is just a double sum with evaluating or taking the samples which are nearby our particular sample location. So this is our currently processed sample where the output will be written, and we are having a neighborhood around samples which are contributing to this sample, and these are weighted by a two-dimensional kernel. So two-dimensional input signal and two-dimensional kernel, where the values of the two-dimensional kernel are then again, for smoothing filters, maybe the value at B00 will be highest, and for the samples which are closer to it, B10 will be higher than, for example, at the ones which are at the diagonal. And maybe everywhere outside, the B is defined as 0. So this is a discrete case where we have our sample representation for both signal and also for the filter kernel. In the continuous case, the convolution of two dimensions can be defined as a multiplication or weighting of our two-dimensional function with a filter kernel which has a certain value multiplied by this infinitely small dx dy squared of our input function. And this infinitely small area is weighted by a certain value of our filter, and this value is then integrated in this into this particular value. So you can see it that while this was previously an area under the curve which was expressing this interval, in this case it will be a volume under such a two-dimensional function which is then weighted with our filter kernel. And we have again a reconstructed function, so an convolution with a discrete set of samples with a continuous filter, and at particular location we will be, which is a non-integer location as well, we will be performing the convolution as a double sum of samples which are weighted by this continuous two-dimensional filter. In this case, we have a continuous filter, which is, I have to first delete because we have a new image here. We have a continuous filter, and we want to reconstruct the function, reconstructed function, continuous function, with this continuous filter from a discrete set of points. So our intention is to reconstruct the value at xy, which is not at integer location. So that would mean that our filter kernel will be weighting this sample with its values 0.3, 0.5, so not 0, 0, because there is no value defined in these samples with where the filter will be 0, 0. Here is 0.3 minus 0.5, and so on. Here we have minus 0.7, 0.5. So we can see that we are going by 1 between here and here. This is the distance 1 between the samples. And this is 1 minus 1.7, and the value is for y 0.5, and so on. So we are having some values of our filter kernel. So I will try to sketch for you just the contours of this filter kernel. Somehow looking like this, maybe one more contour. So, and these values are not from the center, but they are values at various locations of this filter kernel, where this filter kernel is intersecting, so to say, the integer locations of our input signal. And then we are taking the values of our filter kernel and weighting with these values our input signal, the neighboring locations, to our non-integer location in 2 dimensions. And summing them up, we will end up in a reconstructed value at this non-integer location, or at any location within this 2D domain. Now, we understand how the convolution works in 2 dimensions for discrete scenario, for continuous scenario, or for the mixed scenario for the reconstruction purposes. Let's have a look at our filters again in 1D so that we have a more clearer understanding. But we already know how to extend it into these higher dimensions. In discrete case, we had our box filter, which was its value was defined at between minus r and r, and its value was then normalized so that the sum of its individual filter values will be equal to 1. So therefore, we had its value was 1 divided by 2r plus 1. Because we have 2r plus 1 set of samples within this discrete filter representation. In case of a continuous box filter, the situation is that we have a discontinuous function. So at particular location, we have suddenly a jump in the function value, and this jump is equal to, is again based on the length of our filter kernel. And so for example, if the length the r will be 1, this height will be 1/2. If the r will be 1/2, as we had previously, our height will be 1. So it will be a square, a box in 2 dimensions. And this filter kernel, however, is defined that it has defined value 1. 1 goes between x is equal to closed interval minus r, r open interval, so that this entire length is equal to this interval is then and it is defined as 0 elsewhere, so x equals to minus infinity open minus r open, or closed interval r plus infinity. So we can see that on one side it is closed, and on another side it is an open interval. The reason of defining the box filter as closed and open on each side of the r distance from 0 is for the reconstruction purposes, because if we will have defined it at both sides, then potentially 2 integer locations can be contributing to a resampled value which is not desired. We want only for this particular filter that only 1 integer location value will be contributing to a box filter type of reconstruction, which is a very crude reconstruction, but in order to it to work properly, here we need to have an open interval. Another filter, which is also used for reconstruction, is the tent filter. And the tent filter will be a filter, as we can see, it is a composition of linear functions, will be used for the linear interpolation. So this box filter previously, if its interval is r is equal to 1/2, it will correspond to the nearest neighbor interpolation. This is its natural radius of the box filter. The natural radius of our tent filter is r equals to 1. And in such a case, it will be a linear interpolation filter. However, the tent filter, if the radius will be differently sized, it doesn't matter. Such a filter is, of course, possible. It will just not be a linear interpolation filtering using a filter with a different extent. However, the tenth filter, if the radius is 1, will have the value 1 at its central location, which will not be the case for different radii of a tent filter. So if we have a radius which is 1.5, then our maximal value of our tent filter will be 2/3. And reciprocally, if our tent filter radius will be 2/3, the central value will be actually higher than 1. And why is this the case? Because the overall area here, the integral of this function needs to be always 1. So that if we are using the filtering with the tent filter, we are not increasing or decreasing values in the output as compared to the output signal. The energy between the input signal and the output signal stays the same. This is secured by the integral of the filter equals to 1. And here we have the cubic B-spline filter, which we had described already before. And this cubic B-spline filter, you can see that its radius is actually 2. So it's defined such that potentially 4 different values of integer values, values at the sampled locations, can contribute to the reconstructed value. And this cubic B-spline filter is defined in this a little bit more complex form, as we can see here. So when it is outside -2, 2, it is 0, that's easy. Then this part, and this part is defined by one cubic function. And this part here, is defined by another cubic formula here. And the advantage of the cubic B-spline filter is that it has the continuity in the first order and also in the second order derivatives. So this is great because it is very, very smooth filter. Its disadvantage is that it doesn't have at the value x equals 0, it doesn't reach the value 1, which means that it is not an interpolative filter. Only interpolative filters will be having the value 1. Like, for example, the tent filter is an interpolative filter. So, and how is this cubic filter created? This cubic filter is created also by convolution. So this is one happy family of filters where the box filter, if it's convolved with itself, it will result into a tent filter. And if you will convolve tent filter with a tent filter, you will result into the cubic B-spline filter. So the cubic B-spline is convolving 4 box filters together, in fact. So this way we understand the correspondence between various filters, where one filter has a radius of 1/2, another filter has radius of 1, and another radius is having the radius of 2. This will lead to the fact that our filtering or reconstruction will be having the best performance but the worst quality with the box filter. The tent filter will be having, as linear interpolation, a reasonable quality, and it will be also reasonably fast. And the cubic B-spline filtering will be the slowest one, but the reconstruction quality will be usually the most appealing one. But filters originating from the box filter are not the only filters which can be considered for reconstruction task. In fact, there are many other filters which can be used for derivative purposes and so on. However, for reconstruction, we will need to talk about other two filters, which one is the Gaussian filter, which is an excellent smoothing filter, which has other very nice properties, and it is based on the exponential function, the Gaussian function, or the normal distribution function as we know it, where we are describing the exponential function by its mean values and by the variance expressed by the sigma. So this filter will have a great smoothing properties, however, and it is also a filter which has with a very good continuity conditions. However, its disadvantage is that it has an infinite support. So it is non-zero over the entire value range on the real value interval. So therefore, its validity would need to be trimmed for or windowed for certain reconstruction tasks. Another filter which can be used for reconstruction purposes would be the Catmull-Rome cubic filter, and this filter is also a cubic filter, as it was the cubic B-spline. However, it is an interpolative filter, as we can see here, unlike, for example, the Gaussian filter, which is not an interpolative one. I forgot to tell you about the Gaussian filter, that in case we will be trimming it, let's say we trim it to the extent -1, there will be some artifacts probably coming from this hard trim, so probably a smooth multiplication with another smoothing filter called window would be probably more desired. So we will have such a function which we will multiply the Gaussian filter with. That will be result in a much smoother transition to 0. But also what we need to do is to renormalize this trimmed interval so that the area within the trimmed interval, under the trimmed interval, is then equal to 1. Otherwise, we will have a filter which will actually be losing energy of our original signal. Back to the cubic Catmull-Rome filter. So it is an interpolative filter, so which means that the reconstruction will go directly through the elements of the samples, the sample values and the values on the reconstructed function will be aligned. However, the other aspect is that in order to get an overall value 1 integral, there is some negative part of this filter. So, which means that this will actually cause a certain effects which will be undesired. Such a filter, when interpolating a certain function, especially a sharp transition function, will result into a certain undershooting or overshooting of this interpolation. So this interpolation property, which is sometimes desired one, will come at a certain expense. We see that the definition of this interpolating Catmull-Rome cubic filter is similar to the cubic B-spline, so it is also separated into 3 intervals in principle, while the intervals -1, 0 and 0, 1 are symmetric, as well as the -1, -2, -1 and 1 and 2. Based on these examples of filters which we have now covered, so the box filter, tent filter, the cubic B-spline, the Gaussian or the Catmull-Ron cubic spline filter, we can see that there are various properties of filters. Some of the filters would be interpolating, meaning that they are the sample values and the reconstructed function are aligned at the integer positions. Some filters will be approximative, like, for example, the Gaussian filter or the cubic B-spline filter. These approximative filters have the disadvantage that they are not aligned with at the integer locations with the sample values and the reconstructed values. However, they have the advantage that they are very smooth. The interpolative filtering will, for example, in case of Catmull-Ron cubic filter, result into these artifacts of overshooting and on both ends when there is a sharp transition in functional value. So we will see that as some kind of a shadowing or ringing artifacts coming into the as a result of the reconstruction. We can use also, for example, the tent filter, and there will be no any overshooting or undershooting, but there will be then a discontinuity between the sample points in the first order derivative, which will be visible and will appear in some flat sense as a result of such a reconstruction. All the filters which we have been discussing have the so-called ripple-free property, which means that you can see the ripple-free is that if we have a constant function here, the constant function is reconstructed as a constant function. So we have constant train of samples of the same value, and the reconstruction between these samples will be resulting in a straight line. If we will be using a Gaussian filter which is trimmed but not normalized, we will end up in a non-ripple free reconstruction with this wavy pattern, which will be undesired. Then we can talk about the continuity of these filters, which is C0, C1, and C2. C0 means that the continuity is continuous in the function, but the first order derivative is already discontinuous. C1 means that the continuity is extended also to the first order derivative, and the C2 property means that the discontinuity is even, or the continuity is even extended to the second order derivative. From those examples we have been covering, the nearest neighbor interpolation you carried out through the box filter or the reconstruction doesn't have any continuity because this is a discontinuous filter. However, the tent filter will be a C0 continuous filter. Cubic B-spline will be actually a C2 continuous filter, while the Catmull-Ron spline will be C1 continuous. And the Gaussian, as you can see that the exponential Gaussian function can be derived as many times as you want, it has in some sense an infinite continuity. However, it has also an infinite support, so which makes it quite impractical for the reconstruction tasks if used as without any trimming. This trimming, however, will come with a certain expense, with a certain artifacts. For several dimensions, there is an aspect of separability. So if we have a filter, we can, two-dimensional filter, we can sometimes separate it as a smaller filter or a simpler filter defined over each dimension. And then the final filter is a product of these lower dimensional filters defined along each dimension. Such filter, for example, can be a bilinear interpolation will be the result of the two interpolations of the two linear interpolations carried out after each other. So we can either define such a filter as one two-dimensional bilinear filter or as two passes of filtering, one filtering along the x dimension and one along the y dimension. Such a separability can be also used for other higher dimensional filters, like, for example, it could be a cubic interpolating or cubic filtering can be extended to bicubic, or for an XYZ, so volumetric representation, it could be even a tricubic representation. When we are talking about the separability, we should keep in mind that the separability doesn't mean that the degree of the filter remains the same. This could be seen, for example, on the tent filter. The two-dimensional tent filter is a linear filter so bilinear interpolation is a linear interpolation only along the axis x and y, but it is not a linear interpolation along other directions. So this filter, which is created by this as a product of two filters of separate directions, and we see its formula here. Imagine that we have 45 degrees between x and y axis, so this direction of filtering. This is a direction where x is equal to y. And in such a case, if we have only the directions where one of the axes is equal to 0, that's not a problem. That's a linear interpolation. But of these axes, we have, for example, in this case, when x is equal to 0, x is equal to y, the 45 degrees, it will end up in actually a quadratic filter across the diagonal. So we have to keep in mind that such a interpolation scheme as, for example, bilinear interpolation will result in a different result if we have a different orientation of the image with respect to the filter. This has a great advantage for the Gaussian filter because that one is symmetric, is circularly symmetric, and its application will then not depend on the orientation of the image, and the result will be result of interpolation will be identical. We can see it here. We see here that if we make a product of two Gaussian filters, each one in each dimension, x and y, we can actually create a filter which has this description, and we see that this exponential function can be put together, because here we see here is a multiplication of the between the two functions e powered by something. So if we put it together, this will result in this reformulation, and this reformulation is basically tells us here that this defines a radius, as you can remember, as an analytical formula for a circle will be defined through this as a quadratic curve will be defined this way. This means that we are resulting, if we are having Gaussian function, separable filter into two filters in along X and Y, we will create still a symmetric filter, so its orientation of the filter or the image will not change anything on the final reconstruction or the final filtering. Let's have a look at what this separability really means, because it sounds like if we decompose the filter into lower dimensional representatives, we are just complicating the entire process. Why not staying in the overall higher dimensional version of such a filter? The reason is simple. At a little expense of some intermediate storage requirements, we can, with such a decomposition, gain a much higher performance in terms of filtering. So if we are filtering in a two dimensions directly, we will need to have access to k-squared neighbors in principle, while if we are filtering first in x dimension and then in y dimension, then we are needing for each dimension only k access to k neighbors. So the result will be 2k, and we have a linear complexity versus quadratic complexity of a two-dimensional filter. So this is a great benefit, which comes at the expense of storing the intermediate representation after one-dimensional filtering, so that we can use it for completing the filtering process across the other dimension. We can see here various applications of filtering operation. Here you can see, for example, in the top left, you can see an application of the identity filter, which just doesn't change the image at all. We can see some box blurring filter, so an averaging with the uniform values in the filter, constant values in the filter, which results in some kind of a quite blurry representation. Another representation, which is a little bit more smooth in a way, is this Gaussian filtering here. And if our filter kernel is, for example, a line like here, then we will create an anisotropic. So this filter is anisotropic, and it will create an anisotropic filtering, which almost looks like that this image, when it has been taken, has been the camera has been moved while the picture has been shot. So you can create various effects this way, or you can even with so-called deconvolution approach, where you will be inverting this filter kernel, you can generate an unconvolved image, meaning that it will be from such a motion not very high quality image. You can generate a better quality image just by applying the inverse operation of such a filter. The same logic is somehow applied to an unsharp masking filter, sharpening filter, where the idea is that there is already some blurriness in the image, and we want to get rid of this blurriness. And how to get rid of it? Maybe we can subtract from our original image a blurred version of itself. You can see it in this formula here, where we are having some value of our original image, which is now amplified beyond its original values by this factor alpha. And then the same factor alpha is used here so that we can subtract that amount, but only of the blurred parts of the image, which is created by this convolution of this original image with the smoothing filter. And we can reformulate this so that we are not performing any subtraction really in our filtering process to create one sharpening kernel, which consists of weights which are associated with the identity filtering minus the smoothing filtering. So here you can see the usefulness of this identity filtering where we are generating then the sharpening filter kernel. Let's go back and discuss the usage of our filtering using convolution for the purposes of image reconstruction. So, for example, we can have various artifacts here. Which I was hinting upon at the beginning of this lecture. We can have various edgy representations. We can have various representations of moire patterns, or in the temporal domain, we can have, for example, this stage coach wheel effect. You can see in our scene here that we have various problems appearing here. For the beginning, we can see that our reconstruction with the nearest neighbor filter is resulting into a lot of staircase artifacts. And in the parts where there is some regular pattern, like for example, in the blinds on these windows, we can see that there are some kind of weird patterns appearing. And these patterns are again the moire patterns. They are non-existent there, but the reconstruction of alignment of the one regular pattern with another regular pattern will result with poor reconstruction scheme into these artifacts. And the same artifacts can be also seen here. First off, there are these edgy structures which are disturbing, and second, they are also resulting into this on the higher level scale features which are appearing here, which are really just a phantom features non-existent in the original data. Let's have a look how we are performing the reconstruction in a practical way. So we typically want to deal with data which is already set in a sampled representation perhaps, and then we want to represent it on another discrete representation for the display purposes, for example. To do that, we can see that we have our first sampled representation of our data, and then we would like to, for example, perform certain super sampling process on this representation. So as a first step, what we do, we reconstruct the original continuous function from our samples using a discrete continuous convolution with our reconstruction filter. And then this function, which is now already continuous, we can sample at a much higher sampling rate. The smoothness of this reconstruction filter needs to have certain extent so that it covers several samples, and it's not too narrow that it will be able to contribute only to take into account only one value, for example. That would not be a good reconstruction filter. A bad reconstruction filtering will be performed, for example, with the nearest neighbor filtering, which will result in something like this. And then, if we will be performing resampling of such a continuous function, we will have these edgy artifacts that are present in the resampled function as well, which would be undesired. Therefore, a higher quality reconstruction filter is crucial for proper resampling, as we call it. So we have here the two conceptual or logical steps where we are performing an reconstruction and then the resampling. So, but first, we have first covered now a situation on the very right where we have a lower resolution input representation, and the output resampling results in a higher density of the samples. What if we have the opposite situation, and out of higher resolution, which we have originally, we would like to create a lower resolution image. So for example, hopefully you can see it well, there are circles of which are indicating the original input sample points, and they are surrounded by their individual original pixels. And then there are these other points, these black points, which are standing for the output desired sample resolution. One could think of, if we have already such a high resolution, why don't we just take the samples which are closest to our desired sample? Why don't we just take this sample value, for example, and not the other values which are more far away? If we would do that, we would create again certain aliasing effects, which the higher resolution will sort of be giving a possibility to have a more higher frequency sort of leaking into a representation which is then sampled by lower frequency samples, and will create a similar artifact as we have seen in the first example of these sine waves, where a high density sine wave was suddenly then turning into or high frequency sine wave was turning into a much lower frequency sine wave with improper dealing with the reconstruction. So you would see, for example, here that in such a case, if we will be performing resampling here with the nearest neighbor, we will be creating that practically large part of this row will be captured in our reconstruction. However, this row will be not contributing to the final outcome at all. Then there will be another row will be contributing to our outcome representation, and the next row as well. And then again, the next row will not. And then again, two rows will be representing our output samples, and then one row will not. And all this then results and generates these moire patterns, which we have been seeing in the previous cases. So these logical two steps of reconstruction and resampling are performed in the following way. First, we have an input samples, either higher or lower sampled than the outcome samples. Then we perform the reconstruction of the continuous function. After we perform the continuous reconstruction function, then in order based on the representation of our samples, in our case here, these samples are much more far away from each other than the input samples, so we need to band limit our reconstructed continuous function so that these details, the maximal detail can be captured. And the maximal detail which can be captured is represented by these samples. It looks like this. So we need to smooth this continuous representation by some smoothing filter. After we smoothen this representation, then we can perform the sampling. And what we can see here is that here is one reconstruction, here is one convolution from the samples happening, here is another convolution from the samples happening, and we know that based on the associative rule in convolution, we can actually convolve these two filters together and perform the reconstruction and band limiting for our outcome sampling in one pass. And this will be this arrow here, where we have these filters pre-convolved together, and then the reconstruction and smoothing is happening in one pass. In fact, between these two filters, one used for the reconstruction purposes and one for the smoothing, both are having the same essential structure. Both would be looking approximately like this, while one is maybe more broad and one is maybe not so broad. And in fact, we can take just the one which is corresponding to the lower resolution. So if our input resolution will be of a lower frequency sampling than the output, then we can take a corresponding reconstruction filter, which could be used then for the resampling purpose as well. So there is no additional smoothing necessary after we perform the reconstruction of this low frequency input into a continuous representation. Then we can directly sample it. However, if we have our lower resolution output and high resolution input, then we would need to perform the band limiting, and actually we can perform the reconstruction then directly with this lower resolution filter, more broader filter kernel, which will then perform the band limiting and reconstruction at the same time. Now, this was all oriented towards practical usage of sampling and reconstruction. And let's have a look at the sampling theory, which is behind all this quality of the reconstruction from a sampled signal. We can see the correspondence of our filters and convolution in the other domain than the spatial domain, namely in the frequency domain. We can turn our input signal, whether it is a input signal of a one-dimensional signal or several-dimensional signal, we can turn a spatial signal into a frequency representation through the so-called Fourier transform, where every single signal can be represented by a sum of differently weighted sine waves with different phase and with different frequency. So we basically stack up several sine waves together in order to create an approximation or a full representation of a particular signal in spatial domain. So how does it look like? The Fourier transform could be used if our desired signal is this kind of a box representation, which is a periodic one. We can represent it by using the one sine wave, and this one sine wave we will then augment with another sine wave of a different frequency and of a different amplitude. And you see that by summing up these two different sine waves, we are already getting reasonably close to our spatial signal. And we have just basically now defined a sine wave of two different frequencies. So we can see it on our frequency spectrum. Here would be the two frequencies and their corresponding intensities or amplitudes. And we can see that even further refining the values of our additional sine waves and additional frequencies, we can get closer and closer to representing a high frequency signal. So this is how we are turning a spatial signal into its frequency representation. And it is called, to decompose this spatial signal into sine waves, is also called Fourier decomposition. And the Fourier transform is used for this purpose. We can see here another example of a even function. So we have been reconstructing with the sine wave an odd function. Here we would have an even function, which is just representing as this box filter. You remember we had the box filter, and this box filter essentially can be represented by a cosine function, and this cosine function is then further and further augmented by other sinusoid functions, so that it's not defined very strongly on the negative side, and its transition from the 0 to 1 gets sharper and sharper. So the slope is, in the first iteration, relatively small, not so steep. Here we have even steeper transition, and even steeper transition. So we can see that with a relatively few functions, we can reconstruct the box filter, or sorry, represent the box filter in the frequency domain. How does the Fourier transform look like? The Fourier transform can be defined in the following way. If we want to transform a spatial signal defined by the function x into its frequency representation, f of u, we perform an integral in the continuous case of this function and product with this exponential function of e powered by 2 pi I u x, so where the u would be here the variable for the frequency domain, and the x is the variable for the spatial domain. Please keep in mind that this strangely new thing of this e powered by something is just nothing else than a sum of cosines and sinusoids, one representing the values for the real part and one representing the value for the imaginary part. So, which is so our signal, our real signal, will end up in a symmetric function, but this symmetric frequency representation might have a complex values. If our input function will be actually a even function, then we will have only real coefficients in our frequency representation. So there will be no sine functions contributing to our Fourier decomposition. The inverse Fourier transform, so getting from the representation in frequency domain back to the spatial domain, can be done in a very similar way. It's just that here in the exponential function we don't have a minus but plus, but other than that, the formula for the transform is the same. It's an integral of the weighted contributions of various sine waves, which is then representing as the spatial signal. There are various interesting properties in this Fourier transform. And I'm sure you have heard about Fourier transform before, so that's why this is just a recapitulation. But some aspects are important here for the purposes of sampling and reconstruction, which we need to highlight. So for example, the square of our Fourier representation and its sum and the square of our functional representation and its integral are the same, meaning that these two areas in this image have the same integral, and meaning that they have the equal energy. Another interesting aspect is that if we are multiplying our function with some constant and then perform a frequency domain transform with Fourier transformation, then we can take out this constant value out of perform the Fourier transform and then multiply the Fourier transformed function instead with this constant. Something interesting is happening inside if we are, for example, stretching or dilating our function in the spatial domain. We will be dilating or stretching this function in the frequency domain. So, which we can see here in this example. Here we have an input signal in orange and its frequency representation. We already said that if we have a real function, its image in the frequency domain will be a symmetric representation. So we see this symmetry here. And this representation, if we will be stretching the function value by dividing the x by half, for example, we will be actually shrinking the frequency response of after the frequency transformation. So a dilation in the spatial domain will result into shrinkage in the frequency domain. In the frequency domain transformation, we have the average value of our values in the spatial domain will be actually resulting in the amplitude at f with this head 0. So this is the average value of our frequency domain representation. You can understand it as some kind of a shift, or if we will be dealing with electric signal, it will be the direct current component, which we will be representing at the positions 0, u equals 0. And now the interesting aspect comes from the frequency domain and spatial domain interrelationships with respect to the convolution. And spatial domain convolution, which is then transformed in the frequency domain, corresponds to frequency domain of the individual functions and a simple multiplication between them. So in other words, if the convolution will be very costly operation, we can simply transform our spatial signal into the frequency domain, then perform, instead of this costly convolution, a very cheap multiplication. And then after we perform the multiplication, we can transform this multiplied output signal back to the spatial domain. And we could be possibly having a lower complexity of our computation by this visiting or transforming the problem the complex problem into a simpler problem in the frequency domain. And this is symmetric because if we have a spatial domain multiplication, then it corresponds to a convolution of two frequency domain representations of the spatial functions. We can see it here on this graph, where we can see that we have one function f and one function g. And if we will be convolving them, these two, that will be the same as, and then performing the frequency domain, it will be the same as multiplying these two. Or if we are multiplying these two functions in the spatial domain, we have the product here, and then we are transforming this product into the frequency domain, it will result into convolution of the frequency domain representations of these two functions, f and g. And this is symmetric, as I said. This is very important for the theory behind linear reconstruction. We can see, for example, here that our frequency domain representation of certain filters are showing up the quality of reconstruction. So, for example, our box filter, which we said is generally a poor reconstruction filter because it has a very small extent and it has a discontinuity, is resulting into a frequency domain image of this filter, which has an infinite extent, and it's called a sinc filter. Let's have a look at how can we actually transform the box filter into a sinc filter. So remember, this is our description of the Fourier transform. Now our function, our box filter, is very simple. It is described here. And we can see that that if we are putting just this constant part of 1 by changing the margins of our integration interval, then we perform here, our function value will be equal to 1. So we have only these exponential function components. And this is a relatively simple function to integrate. So if we perform the integration, this will be the result of the integration. And at the same time, what we know is that the correspondence between the sine function and the e powered by something function. So this term here is equal to sine pi u. And we can see that actually this term is appearing here is slightly turned because here is minus. But 2i is also here, and these two terms are also here. So actually we can we see that this integration and the Fourier transform results into this function sine pi u divided by pi u, which is actually known as the sinc pi u. And this is the sinc pi u filter, which looks like a cosine, which is gradually having lower and lower curviness, and it's always at each position where it is going through the y equals 0 or x axis, it actually is going through an integer position. More about that later. You can now see that if we are performing a filtering with the 10th filter, we have a sinc squared. It will be its frequency representation. And it's a thinner filter you can see here in the frequency domain. its frequency domain response is not so extensive, doesn't have infinite support, or does have, but it's a much smaller contribution for higher frequencies. Even more so, that holds for the cubic B-spline filter, which results into the sinc powered by 4 function. And here we have the Gaussian function, and the Fourier transform of a Gaussian function is another Gaussian function, but with a different kernel size, or both have infinite extent, of course, but they will one will be having values close to 0 much faster than the other one. So the more broader one Gaussian filter is, let's say in the spatial domain, the more shrinked representation of the Gaussian we will have in the frequency domain. Now we know that we can transform the signals of known reconstruction filters into the frequency domain. So we can now, instead of convolving in the spatial domain, we can actually multiply with these reconstruction values in the frequency domain. And that multiplication can be carried out much faster, or can be much more intuitive on what is happening with the signal. And then we have also, remember our Dirac impulse, which is our identity operation for the convolution. Its Dirac impulse is its representation. It can be used for creating something with what we call a comp filter. So we do not have only one Dirac impulse at the position 0, but we actually have a periodic representation of such a Dirac impulse many times. And we call such a filter at integer positions, or at certain distances, equal distance from each other. And we call such a filter a comp filter, because it looks like a comp a little bit. And we can also call it an impulse train, for example. So a frequency representation of such a comp filter is another comp filter. So here we have a frequency representation of that filter. And the more sparse the filter is in the spatial domain, the more dense the filter will be in the frequency domain, and vice versa. We can see here the definition of our comp filter, or the impulse train, being the sum of the impulses, but with of several infinite amount of impulses, and displaced from each other by some period t. Now let's have a look at the sampling and reconstruction from the perspective of the machinery which we have learned on this lecture, or which we have recapped during this lecture. Let's just have a look at our image of these branches, and let's just have a look at just one scan line, one-dimensional representation of our signal. So such a scan line will correspond to different intensity values along this scan line, as depicted here on this line plot. This representation, this signal, can be transformed with a Fourier representation into this representation, where we can see that there is some direct current component, which is the average value, which will be something like this here, and then there are other frequencies represented with lower and lower frequencies, and these frequencies are represented are resulting in a symmetric spectrum because our function is a real valued function at the input. Now, this is a continuous function at this very moment. So this is a reality, if you like. And we can sample this reality with our, and the sampling essentially corresponds to a identity transform or the identity operation at a certain particular locations. So the sampling is realized with this direct, with this Dirac impulse train, which we have been talking about. So the Dirac impulse train is creating this sampling. So here we have a multiplication of a signal with the Dirac impulse, and this multiplication with this impulse train is resulting into a in the frequency domain is resulting into convolution with the Dirac impulse train of our frequency spectrum. This convolution, therefore, generates us an identity transform of our frequency spectrum, which will result into copying the spectrum multiple times in the frequency domain. And depending on how frequently we sample, how dense the sampling is, the more far away these frequency responses will be from each other. So the more dense the sampling is, the more far away this frequency response is. So these peaks of these other spectral copies will be more far away from each other. The reconstruction, in principle, is just a multiplication of a filter. So we can see here some filter, for example, looking like this, which is a frequency representation of our reconstruction filter, is a multiplication of a filter with our frequency representation. And in case of the filter is very low quality, like for example, here this will be the sink in the frequency domain, which corresponds to the box filter in the spatial domain, we will get a reconstruction out of our samples of a function which has this nearest neighbor interpolation, and we will see these edgy artifacts of the reconstruction here in this image. So this is the pipeline of performing the sampling and reconstruction, what is happening with the signal in the frequency domain. And we can see suddenly that there are certain phenomena happening here, like for example, generation of these aliasing spectra. And these aliasing spectra, when they will be very close to each other, they will be overlapping, which means that the one frequency response, which is our original function, will be combined, will be summed up with another, with itself, so that there will be these aliasing frequencies represented, which will then show on the final image. And as I said, the more closer the sampling is, the more far away these copies of the spectra will be from each other, and we want them to be possibly far away. You can see that we have been using here for here the multiplication is with the sink filter, and you can see that somehow this frequency is coming from the second aliasing spectrum in the negative direction, and here this part is the aliasing from the positive copy of our frequency response. So once again, the sampling, which is a multiplication of a comb filter in the spatial domain, is a convolution with the comb filter or its frequency domain representation of the comb filter in with the frequency domain of the signal. I have already mentioned this several times, therefore I'm skipping this slide, but you have it for complete. And the same is here, just that you can read about the reconstruction with the box filter in the spatial domain and which is the sync filter in the frequency domain. And in this slide, we can see how can we mitigate the problem of the bad sampling. So the sampling multiplication with our comb filter in the spatial domain, here it is, the sampling is not performed in on a very dense, in a very high frequency. The situation, therefore, the aliasing spectra in the frequency domain are very close to each other. They are very close to each other. But if we are increasing the sampling rate, which is the double sampling rate shown here, we can see that the aliasing spectra are getting more far away from each other. And if we have a band limited signal, then at some point there are only certain frequencies which are present. So there is a certain amount of frequencies which are non-zero in a compact form around the zero frequency, and then outside this interval there is zero if we have a band limiting. And the best situation will be to have the sampling at such a frequency that that we push out the aliasing spectra beyond the area of our band limited range of frequencies. So here, in such a case, as we have in this case of sampling, our function, reconstruction function, can relatively simple be performed in the frequency domain, where we are multiplying the frequency response of our filter with this frequency response of the signal, and meaning that we are performing the convolution in the spatial domain. We are coming back to the beginning, where we stated that we need a certain Nyquist frequency corresponding to a certain sampling rate. So our function, which we are sampling, cannot exceed a certain presence of frequencies, and it should have only certain interval of frequencies. But sometimes we cannot influence the sampling rate because our camera sensor has just a certain resolution and we cannot increase it. Therefore, it is important that we are band limiting the input signal. Band limiting would mean that we are pre-filtering our signal so that we are putting some frequencies to be equal to zero. And by that, what it means that we are disregarding certain high frequencies. Our image will get more low pass filtered or blurry, if you like, but we will be able to represent such a representation with our filtering scheme. So, and the less amount of samples we can afford, the smaller this band limiting filter kernel radius can be, resulting in more and more blurred image. Only after the band limiting, we can be sure that this band limited function can be represented reasonably well with the given amount of samples. So after we have performed band limiting or not, we have resolved our image in a certain sampling, which is shown here um, of our scene, and that corresponds to certain frequency representation, with our signal being replicated several times in this frequency domain. Now, if we will be performing a filtering or reconstruction with the box filter, which will be very narrow, which means that it will be very broad in the frequency domain. So everything what is narrow in the spatial domain will be broad in the frequency domain, and vice versa. Then our reconstruction filter, which means that we want to just take out this one frequency response with our reconstruction kernel and multiply it. The best would be just to cut it out with a perfect sort of box filter in the frequency domain and have it not leaking in any of the aliasing spectra. But with nearest neighbor interpolation, this will not be the case, and there will be a lot of aliasing spectra leaking into our reconstruction or reconstructed representation. If we are performing the linear interpolation with the tent filter, the situation will be much better. The support of the filter will be much smaller generally. There will be also still some aliasing effects happening, so which of course we can see here as the discontinuities in the first order derivatives. And we can see that if we have let's say a cubic filter, like in the lowest case, the reconstruction will have the frequency domain representation of our reconstruction filter will have the smallest extent. It will be the narrowest one, although maybe theoretically it has the infinite support, but it goes pretty quickly to zero after being more far away from the u equals to 0 value. And we can see perhaps here that the reconstruction quality is the best. If you want to see the reconstruction quality, I suggest that you look on the web and at the book and compare these images between each other. So in theory, the most effective reconstruction filter for us will be in the frequency domain, a box filter, which will be then in the spatial domain, a sinc filter, which unfortunately has in the spatial domain an infinite support. So it will be impossible to perform the convolution of the sinc filter with the input signal. We can do it in the frequency domain. So if we want to have an ideal reconstruction with the box filter in the frequency domain, then we can perform it in the frequency domain and then transfer the signal back to the spatial domain and have a perfect reconstruction of our sampled representation of our input function. And that would be all for today about sampling and reconstruction, which is very crucial to understand various aliasing effects which are occurring in computer graphics, but in any domain where we are dealing with a signal which is for the purposes of processing on a computer, first discretized into sampled representation and then perhaps resampled and reused again, and what can be the various artifacts which are happening during this process. Thank you very much for your attention for today, and see you at the next lecture. Goodbye.